Just give me a few seconds. So I marked your papers, your mid-sem papers, guys, and I handed it over to Professor Sarasinghe, your coordinator. So you can request your marks from him. Just send a request maybe, and he might share it with you all. So the process is I can't share it with you all. You can get it from him directly. I've submitted the marks to him. So just please make note of that and tell your other batchmates as well. Okay. Right. So today and next week will be the last lecture. Today's lecture and next week. Next week will be the last lecture. If we have more time, we can definitely do practice questions. I've uploaded a few things to the Google Drive as well. For example, if you go to model paper, I have uploaded another model paper that you all can have a look at and answer. And I put some questions in the questions and the answers as well, similar to the first model paper as well. And then from problems and solutions, I've given for lecture 9 as well. That's today's lecture. I've given a couple of problems there and solutions for those problems as well. So as I will upload few more problems for the remaining lectures because I've only put up 7, 9, 4, and 5. But in the lectures also you will find more problems. And if you go to the reference material, Shom's Introduction to Mathematical Economics, that will also have a lot of problems. And I encourage you to try out all these problems. So mid-sem paper is also uploaded. I don't know whether you all went through it, the answers as well. And then, yeah, those are the things, lectures, obviously. So in the course outline, we are now we're going to study economic dynamics and integration. So today's lecture is continuation of calculus, where we'll be studying integration. And next week, I'll be covering very briefly differential equations. And then we'll be done with the lectures. So that's the course outline. So before I go into today's lecture, which is mainly covering integration, I thought we'll start off by watching 3 Blue 1 Brown's video on what he has to say on the intuition behind what we do in integration. I think that's important to understand before we get into the algebraic solving and computations. So we'll watch this video and then we'll come and do the lecture. Sorry, I haven't shared the screen.
That it feels reasonable and preferably obvious, at least at an intuitive level. In this video, I want to talk about integrals, and the thing that I want to become almost obvious is that they are an inverse of derivatives. Here, we're just going to focus on one example, which is a kind of dual to the example of a moving car that I talked about in chapter 2 of the series, introducing derivatives. Then in the next video, we're going to see how this same idea generalizes, but to a couple other contexts. Imagine that you're sitting in a car and you can't see out the window. All you see is the speedometer. At some point, the car starts moving, speeds up, and then slows back down to a stop, all over the course of 8 seconds. The question is there a nice way to figure out how far you've traveled during that time based only on your view of the speedometer? Or better yet, can you find a distance function, s of t, that tells you how far you've traveled after a given amount of time, t, somewhere between 0 and 8 seconds? Let's say that you take note of the velocity at every second, and you make a plot over time that looks something like this. And maybe you find that a nice function to model that velocity over time in meters per second is v of t equals t times 8 minus t. You might remember, in chapter 2 of the series, we were looking at the opposite situation, where you knew what a distance function was, s of t, and you wanted to figure out the velocity function from that. There, I showed how the derivative of a distance versus time function gives you a velocity versus time function. So in our current situation, where all we know is velocity, it should make sense that finding a distance versus time function is going to come down to asking what function has a derivative of t times 8 minus t. This is often described as finding the antiderivative of a function. And indeed, that's what we'll end up doing. And you could even pause right now and try that. But first, I want to spend the bulk of this video showing how this question is related to finding the area bounded by the velocity graph, because that helps to build an intuition for a whole class of problems, things called integral problems in math and science. To start off, notice that this question would be a lot easier if the car was just moving at a constant velocity, right? In that case, you could just multiply the velocity in meters per second times the amount of time that has passed in seconds, and that would give you the number of meters traveled. And notice, you can visualize that product, that distance, as an area. And if visualizing distance as area seems kind of weird, I'm right there with you. It's just that on this plot, where the horizontal direction has units of seconds, and the vertical direction has units of meters per second, units of area just very naturally correspond to meters. But what makes our situation hard is that velocity is not constant. It's incessantly changing at every single instant. It would even be a lot easier if it only ever changed at a handful of points, maybe staying static for the first second, and then suddenly discontinuously jumping to a constant 7 meters per second for the next second, and so on, with discontinuous jumps to portions of constant velocity. That would make it uncomfortable for the driver. In fact, it's actually physically impossible, but it would make your calculations a lot more straightforward. You could just compute the distance traveled on each interval by multiplying the constant velocity on that interval by the change in time, and then just add all of those up. So what we're going to do is approximate the velocity function as if it was constant on a bunch of intervals. And then, as is common in calculus, we'll see how refining that approximation leads us to something more precise. Here, let's make this a little more concrete by throwing in some numbers. Chop up the time axis between 0 and 8 seconds into many small intervals, each with some little width dt, something like 0.25 seconds. Now consider one of those intervals, like the one between t equals 1 and 1.25. In reality, the car speeds up from 7 meters per second to about 8.4 meters per second during that time. And you could find those numbers just by plugging in t equals 1 and t equals 1.25 to the equation for velocity. What we want to do is approximate the car's motion as if its velocity was constant on that interval. Again, the reason for doing that is we just don't really know how to handle situations other than constant velocity ones. You could choose this constant to be anything between 7 and 8.4. It actually doesn't matter. All that matters is that our sequence of approximations, whatever they are, gets better and better as dt gets smaller and smaller. That treating this car's journey as a bunch of discontinuous jumps in speed between portions of constant velocity becomes a less wrong reflection of reality as we decrease the time between those jumps. So, for convenience, on an interval like this, let's just approximate the speed with whatever the true car's velocity is at the start of that interval, the height of the graph above the left side, which in this case is 7. So in this example interval, according to our approximation, the car moves 7 meters per second times 0.25 seconds. That's 1.75 meters, and it's nicely visualized as the area of this thin rectangle. In truth, that's a little under the real distance traveled, but not by much. And the same goes for every other interval. The approximated distance is v of t times dt. It's just that you'd be plugging in a different value for t at each one of these, giving a different height for each rectangle. I'm going to write out an expression for the sum of the areas of all those rectangles in kind of a funny way. Take this symbol here, which looks like a stretched S for sum, and then put a 0 at its bottom and an 8 at its top to indicate that we'll be ranging over time steps between 0 and 8 seconds. And as I said, the amount we're adding up at each time step is v of t times dt. Two things are implicit in this notation. First of all, that value dt plays two separate roles. Not only is it a factor in each quantity that we're adding up, it also indicates the spacing between each sampled time step. So when you make dt smaller and smaller, even though it decreases the area of each rectangle, it increases the total number of rectangles whose areas we're adding up, because if they're thinner, it takes more of them to fill that space. And second, the reason we don't use the usual sigma notation to indicate a sum is that this expression is technically not any particular sum for any particular choice of dt. It's meant to express whatever that sum approaches as dt approaches 0. And as you can see, what that approaches is the area bounded by this curve and the horizontal axis. Remember, smaller choices of dt indicate closer approximations for the original question. How far does the car actually go? So this limiting value for the sum, the area under this curve, gives us the precise answer to the question in full unapproximated precision. Now, tell me that's not surprising. We had this pretty complicated idea of approximations that can involve adding up a huge number of very tiny things. And yet, the value that those approximations approach can be described so simply. It's just the area underneath this curve. This expression is called an integral of v of t, since it brings all of its values together. It integrates them. Now at this point, you could say, how does this help? You've just reframed one hard question, finding how far the car has traveled, into an equally hard problem, finding the area between this graph and the horizontal axis. And you'd be right. If the velocity-distance duo was the only thing that we cared about, most of this video, with all of the area under a curve nonsense, would be a waste of time. We could just skip straight ahead to finding an antiderivative. But finding the area between a function's graph and the horizontal axis is somewhat of a common language for many disparate problems that can be broken down and approximated as the sum of a large number of small things. You'll see more in the next video, but for now I'll just say in the abstract that understanding how to interpret and how to compute the area under a graph is a very general problem-solving tool. In fact, the first video of this series already covered the basics of how this works. But now that we have more of a background with derivatives, we can actually take this idea to its completion. For our velocity example, think of this right endpoint as a variable, capital T. So we're thinking of this integral of the velocity function between 0 and t, the area under this curve between those inputs, as a function, where the upper bound is the variable. That area represents the distance the car has traveled after t seconds, right? So in reality, this is a distance versus time function, s of t. Now ask yourself, what is the derivative of that function? On the one hand, a tiny change in distance over a tiny change in time, that's velocity. That is what velocity means. But there's another way to see this, purely in terms of this graph and this area, which generalizes a lot better to other integral problems. A slight nudge of dt to the input causes that area to increase, some little ds represented by the area of this sliver. The height of that sliver is the height of the graph at that point, v of t, and its width is dt. And for small enough dt, we can basically consider that sliver to be a rectangle, so this little bit of added area, ds, is approximately equal to v of t times dt. And because that's an approximation that gets better and better for smaller dt, the derivative of that area function, ds dt, at this point equals vt, the value of the velocity function at whatever time we started on. And that right there, that's a super general argument. The derivative of any function giving the area under a graph like this is equal to the function for the graph itself. So, if our velocity function is t times 8 minus t, what should s be? What function of t has a derivative of t times 8 minus t? It's easier to see if we expand this out, writing it as 8t minus t squared, and then we can just take each part one at a time. What function has a derivative of 8 times t? Well, we know that the derivative of t squared is 2t, so if we just scale that up by a factor of 4, we can see that the derivative of 4t squared is 8t. And for that second part, what kind of function do you think might have negative t squared as a derivative? Well, using the power rule again, we know that the derivative of a cubic term, t cubed, gives us a square term, 3t squared. So if we just scale that down by a third, the derivative of 1/3 t cubed is exactly t squared. And then making that negative, you'd see that negative 1/3 t cubed has a derivative of negative t squared. Therefore, the antiderivative of our function, 8t minus t squared, is 4t squared minus 1/3 t cubed. But there's a slight issue here. We could add any constant we want to this function, and its derivative is still going to be 8t minus t squared. The derivative of a constant just always goes to 0. And if you were to graph s of t, you could think of this in the sense that moving a graph of a distance function up and down does nothing to affect its slope at every input. So in reality, there's actually infinitely many different possible antiderivative functions, and every one of them looks like 4t squared minus 1/3 t cubed plus c for some constant c. But there is one piece of information that we haven't used yet that's going to let us zero in on which antiderivative to use: the lower bound of the integral. This integral has to be 0 when we drag that right endpoint all the way to the left endpoint, right? The distance traveled by the car between 0 seconds and 0 seconds is, well, 0. So, as we found, the area as a function of capital T is an antiderivative for the stuff inside. And to choose what constant to add to this expression, what you do is subtract off the value of that antiderivative function at the lower bound. If you think about it for a moment, that ensures that the integral from the lower bound to itself will indeed be 0. As it so happens, when you evaluate the function we have right here at t equals 0, you get 0. So in this specific case, you actually don't need to subtract anything off. For example, the total distance traveled during the full 8 seconds is this expression evaluated at t equals 8, which is about 85.33, minus 0. So the answer as a whole is just 85.33. But a more typical example would be something like the integral between 1 and 7. That's the area pictured right here, and it represents the distance traveled between 1 second and 7 seconds. What you do is evaluate the antiderivative we found at the top bound, 7, and then subtract off its value at that bottom bound, 1. And notice, by the way, it doesn't matter which antiderivative we chose here. If for some reason it had a constant added to it, like 5, that constant would just cancel out. More generally, anytime you want to integrate some function, and remember, you think of that as adding up values f of x times dx for inputs in a certain range, and then asking, what does that sum approach as dx approaches 0? The first step to evaluating that integral is to find an antiderivative, some other function, capital F, whose derivative is the thing inside the integral. Then, the integral equals this antiderivative evaluated at the top bound minus its value at the bottom bound. And this fact right here that you're staring at is the fundamental theorem of calculus. And I want you to appreciate something kind of crazy about this fact. The integral, the limiting value for the sum of all of these thin rectangles, takes into account every single input on the continuum from the lower bound to the upper bound. That's why we use the word integrate. It brings them all together. And yet, to actually compute it using an antiderivative, you only look at two inputs, the top bound and the bottom bound. It almost feels like cheating. Finding the antiderivative implicitly accounts for all of the information needed to add up the values between those two bounds. That's just crazy to me. This idea is deep, and there's a lot packed into this whole concept. So let's just recap everything that just happened, shall we? We wanted to figure out how far a car goes just by looking at the speedometer. And what makes that hard is that velocity is always changing. If you approximate velocity to be constant on multiple different intervals, you could figure out how far the car goes on each interval just with multiplication, and then add all of those up. Better and better approximations for the original problem correspond to collections of rectangles whose aggregate area is closer and closer to being the area under this curve between the start time and the end time. So that area under the curve is actually the precise distance traveled for the true nowhere constant velocity function. If you think of that area as a function itself with a variable right endpoint, you can deduce that the derivative of that area function must equal the height of the graph at every point. And that's really the key right there. It means that to find a function giving this area, you ask, what function has v of t as a derivative? There are actually infinitely many antiderivatives of a given function, since you can always just add some constant without affecting the derivative. So you account for that by subtracting off the value of whatever antiderivative function you choose at the bottom bound. By the way, one important thing to bring up before we leave is the idea of negative area. What if the velocity function was negative at some point, meaning the car goes backwards? It's still true that a tiny distance traveled ds on a little time interval is about equal to the velocity at that time multiplied by the tiny change in time. It's just that the number you'd plug in for velocity would be negative, so the tiny change in distance is negative. In terms of our thin rectangles, if a rectangle goes below the horizontal axis, like this, its area represents a bit of distance traveled backwards. So if what you want in the end is to find a distance between the car's start point and its end point, this is something you're going to want to subtract. And that's generally true of integrals. Whenever a graph dips below the horizontal axis, the area between that portion of the graph and the horizontal axis is counted as negative. And what you'll commonly hear is that integrals don't measure area per se, they measure the signed area between the graph and the horizontal axis. Next up, I'm going to bring up more context.
Okay, so I wanted you all to watch that particular video because three blue, one brown basically covers the whole lecture within 17 minutes. And it's good for you to hear the same kind of words um, over and over again and get familiarized with it if you're not very familiar. Now, what you have to understand here is this is a continuation from our differentiation lesson. And you saw that in integration, we talk about this antiderivative because we calculated derivatives under differentiation. Now we are going to calculate antiderivatives. And there are specific rules, just like for in the differentiation lesson, we have specific rules under integration. There are techniques used to calculate integration, and most importantly, you should ask, why are we studying integration? We're studying integration mainly because the next lecture is differential equations. Under differential equations, when you're solving differential equations, you need to have a knowledge on integration. And differential equations come up in larger models, which I have mentioned before, such as dynamic, stochastic, general equilibrium models used by central banks. So differential equations are used there. And to solve these differential equations, you would have to have the knowledge of integration. Of course, you can use MATLAB or Python or R to solve these, but it's very important. What we are doing here is understanding the back end of it. From coding, you do the front end. This is the back end. Right, so we'll get into the lecture. So here we are talking about economic dynamics and integral calculus. So if you read this, what I'm saying here is we have two kinds of economic analysis. One is static analysis, that is your usual equilibrium analysis, demand equals supply or whatever the market equilibriums that you study. And then you have dynamic analysis, right? So you have static and dynamic analysis when you consider economic analysis. So under static analysis, you would study your equilibrium models. Um, and under dynamic analysis, this is where you would consider temporal or the time factor when you're studying dynamic analysis. Dynamic means it changes with accordance with time. So under dynamic models, we have something called difference equations. We have something called difference equations, and we have something called differential equations. Differential equations. So what is the difference between these two types of equations? Difference equations, as I've said here, belongs to discrete time. What do I mean by saying discrete time? You would say, example, 1 second, second, third second, likewise, or minute or hour or whatever, right? It's discrete, it's countable, 1, 2, 3. Differential equations are continuous time. That's what you saw in the video, the car movement, where we were studying about the velocity and the distance of the car travel during a given time, continuous time. So that is an example of a differential equations. And when you're solving differential equations, we use the knowledge of integration. So that's what I've said here. Integration is a fundamental mathematical operation that plays a central role in dynamic analysis. And let's get into what this whole topic of integration is. So in integration, we are talking about this concept called antiderivative, or antiderivative, right? So I've said here the definition, if you go through this, the definition, I'm saying let fx be a continuous function. An indefinite integral of f, so I'm saying an indefinite integral of a function simple f with respect to x is a function capital F of x such that, now we are talking about an indefinite integral of some function simple f with respect to x is a function capital F of x such that when you differentiate this capital F of x, that's what I've written here, f prime of x. In other words, this, when you differentiate your capital F of x, you should get your simple f of x, right? So here, what we're doing is what we have learned before is this aspect. Now we are going to learn, so we are going to convert this now. We are going to find f of x such that, how do we do that? We integrate simple f of x with respect to dx, right? So these are operators, integration, differentiation, these are operators. Take this analogy is you have your additions and your subtraction, right? So similarly here you have your derivative, which is what we talked about here, and then you have your antiderivative, which is what we talk about over here, right? So what's important is when we are integrating simple f of x with respect to dx, we have a family of functions, and that's what you must have seen in the video as well. We'll get to examples and then you'll understand. we usually, when we don't have those upper and lower bounds that three blue one brown in his video explained, when we don't have those, we usually put a constant, right? So C here is a constant. Let's look at an example. That's the best way to look at this. So I've taken this particular example. Um, you integrate 2x with respect to dx. What do we get? So here we will look at the rules of integration, but here we would get a function x squared plus c. C is a constant. Let's look at x squared. Let's look at differentiating x squared with respect to x. What do we get? 2x, right? So what are we ideally doing? We are finding the antiderivative for 2x, which is x squared. We are basically working ourselves backwards. But why is this constant important? That is because even if I were to differentiate x squared plus 1, I get 2x. If I differentiated x squared plus 1005, I still get 2x, right? So the antiderivative of 2x is not simply x squared, it's x squared plus any other constant value. So hence why we put this constant over here. So we are trying to figure out antiderivative functions through integration. That's what we are doing. It's a different type of operator. Right, so when we're talking about integration, similar to differentiation, we have basic rules. What's the first rule? We'll first look at linearity. So first we have linearity. So what does linearity say? It says the integral of a sum is the sum of integrals, and constants can be pulled out for any functions f of x and g of x and constants a, b. So if I have simple a times f of x plus simple b times g of x. So f of x and g of x are continuous functions. A and b are constants. If I have to integrate this, linearity tells me, look, you can separate out the two. So the integral of this sum is the sum of integrals. So that means I can separate these two out like this. G of x dx, and I can go a little bit further because a and b are constants. I can take it out of the integral sign and simply integrate. Take b out of the integral sign and integrate g of x with respect to dx. That is what linearity is telling me. Then I have something called the power rule. That's the second one. Power rule. So what does the power rule tell me? It tells me if I have a function x to the power n and I want to integrate it with respect to dx, what I would get is x to the power n plus 1 divided by n plus 1 plus c, but there's a condition, n can't be equal to minus 1. Now, this is very straight. This is also something that you've seen before. Why is that? Because we are trying to find the antiderivative of xn and we get this. But if we were to find the derivative of x to the power n plus 1 divided by n plus 1 plus c, how do we go about doing this? Well, you take 1 over n plus 1 out, and you know you have to differentiate x to the n plus 1. Constant, when you differentiate it, it's 0, so I'm going to leave that out. So it's 1 over n plus 1 times, how do we differentiate x to the power n plus 1? You take n plus 1 out, times x to the n plus 1 minus 1. So then n plus 1 cancels out. Why? Because n is not equal to minus 1. And then we are left with x to the power n, right? So what have we done? What we are basically doing is finding the antiderivative of this, which equals to this, and that is what we do through integration, right? Earlier we studied differentiation, and that difference is very important to understand. So there is the power rule. So if you want to integrate any x to the power n where n is not equal to minus 1, you simply add n plus 1 and you divide it by n plus 1. That's the power rule. And an example for this I've given. So if you want to integrate x squared dx, what do we do? So we first check, is n equals to 1 minus 1? No, it's not. It's 2. So here n is equal to 2. Then what is the rule? What does the power rule tell me? Okay, take 2, which is n equals to plus 1 divided by n plus 1. 2 plus 1. And don't forget the constant. Right, so then what do I get? X cube over 3 plus c. Right, so do it backwards also and see. What if I were to differentiate x cube over 3 plus this constant? Now I know constant, when I differentiate it with respect to x, it's 0. I don't have to worry about that. So I only have to differentiate x cube over 3. And even x cube over 3, I take 1 over 3 out, and then I differentiate x cube, I get 3x squared. Then 3 cancels out, I get x squared. Now I know what I have done before is correct, and that's very important. Right. Then that's example number 1. Example number 2, what have I taken? X to the power minus 2. That's also fine. I want to integrate x to the power minus 2. Okay. First, I have to check whether n is equals to minus 1. No, it's not. N is not equal to minus 1. N here is equal to minus 2. Right. So if I were to integrate this, what do I do? X to the power minus 2 plus 1 divided by minus 2 plus 1. Don't forget the constant. Then what do I get here? X to the power minus 1 divided by minus 1 plus c. So x to the power minus 1 is 1 over x. I say 1 minus 1 over x plus c. Right? And just to check whether what I have done is correct, I would differentiate what I have got here. And if I were to differentiate the constant against 0, minus 1 over x, if I were to differentiate, I get minus 1 over, I would get, this is differentiating x to the power minus 1 minus, right? So I would get minus 1 is there, times minus 1, x to the power minus 1, minus 1, right? Don't forget how differentiation goes. So this here makes it plus 1. So I get x to the power minus 2, right? So then from that I know I have done, I found my antiderivative correctly for the function x to the power minus 2, which is this answer. So that's the second rule. What is the third rule? The constant rule. Right? The constant rule. So in the constant rule, if you were to integrate a constant with respect to dx, you would get ax plus c. Now, why is that? Because, again, if I were to differentiate this side with respect to x, ax plus c, what do I get? I can take a out, differentiate dx, x with respect to dx, plus differentiate c with respect to dx. Here I would get a plus 0, and hence I get a. So if I were to integrate a, I get ax plus c. Another way to look at this would be a dx. Actually here it's a x to the power 0 dx, and you can take a out, and I am to integrate x to the power 0 dx, because x to the power 0 is 1, because x to the power 0 equals to 1. So then I can integrate this. Why? Because n is not equal to minus 1. That was the first ruling. Over here on your left hand side, n is not equal to minus 1. So therefore I can take x to the power 0 plus 1 divided by 0 plus 1, and therefore plus c. Then I get ax plus c. So it's another way of looking at it. So that's the constant rule. Then we have the exponential and logarithmic functions. Right, so that's the fourth one. That's the fourth one. The exponential exponential and logarithmic functions. Right, so what are we told over here? So let's look at the first one. We are asked to, this is the first one, integrate the function e to the x with respect to dx. So according to the rule, it says if you were to integrate e to the power x with respect to dx, you again get e to the power x plus c. That's the beauty of this exponential function, because if you remember in differentiation also, if you were to differentiate and find the derivative of e to the power x, you still get e to the power x. Similarly, if you were to integrate e to the power x with respect to dx, you get e to the power x plus a constant value. So that's a very interesting function. Then you have a slightly different one, e to the power a times x dx, where a is a constant, a is a constant, and a is not equal to 0. Okay, so in this one, what do we have? E to the power ax dx, the ruling says if you were to integrate this, you get 1 over a times e to the power ax plus c. Okay, so why is that? So again, differentiate this function and see. So if you were to differentiate it with respect to dx, it's 1 over a e to the power ax. You take 1 over a out, and you want to differentiate e to the power ax with respect to x. So what is that? It's 1 over a times a times e to the power x. So then a to a cancels out. Why is that? Because a is not equal to 0. And you're left with e to the power ax. So you're right. Right? So the antiderivative of e to the power ax is 1 over a times e to the power ax plus c. Then you have finding the antiderivative of 1 over x dx, and that is simply log x plus c, right? Because if you remember, if you were to differentiate log x, what did we get? We got 1 over x. So if you were to find the antiderivative of 1 over x, or the integral, you get log x plus c. So I interchangeably use this. I say find the integral of 1 over x, or I say find the antiderivative of 1 over x. And the answer to that is log x plus c. Okay, these trigonometric functions, you don't need to really bother about that. That is just there for completeness, as I've said here. You don't need to worry about trigonometric functions. Two more rules that you would have to, it's good to keep in mind, but we will also be proving it, is these integrals of some common economic growth related ones. So we have two important functions of integrals that we need to know. One is if you have a function f of x which is equal to a to the power x, where a is a positive constant, right? So 2, 4, 5, any positive constant. So if you are asked to find the integral of this function ax, the answer you get would be a to the power x divided by log a plus c. Okay, and what you have to remember is a to the power x, how it's written in exponential format. A to the power x is also written as e to the power x log a. So from that you can prove this particular answer, this one. And the second one is this second one. First one is over here. Second one is finding the antiderivative for log x. And the antiderivative or the integral of log x is given by x log x minus x plus c. Again, this will also be proved as we go along. Right. So there were a lot of rules that we looked at. What were they? That's what I have summarized over here. So first thing is, if you were to integrate 0, that's simply a constant. If you were to integrate 1, which is a constant value, you get x. So what I've said here is also important. If you were to integrate 1 with respect to dx, so what is 1? 1 is actually x to the power 0. X to the power 0 dx. So that is x to the power 0 plus 1 divided by 0 plus 1 plus c. That is x plus c, right? So I've not put the constant. That's a mistake on my end. Now, always we've been looking at with respect to x. Don't forget, if I give something like this, integrate or find the antiderivative of 1 with respect to dt, simply what I'm looking at is t to the power 0 dt, and that is t to the power 0 plus 1 divided by 0 plus 1 plus c, which is t plus c. So don't worry about what is here, that variable, okay? Because what you need to understand is the concept, and don't make small mistakes where you actually don't look at what the variable is and you simply just do in terms of x, right? So what simple mistakes you can do is, because if you're not familiar with this, is if I give this problem, integrate 1 dt, you would simply do, oh, I know this, it's simply x plus c, right? Because you're so used to writing it in terms of x. And this is absolutely wrong. And I won't give marks for this because you have not, because it's a very simple one and you have not identified what the variable is. And the correct answer would be t plus c. And that's the correct answer. So for that, identifying the variable and the rule used, you get the marks there. Okay, that's one. And then we looked at more generalized version, x n. If I were to integrate this, you get xn plus 1 divided by n plus 1 plus c, right? That's also done. And then 1 over x is equal to log x. When we integrate 1 over x, when we integrate exponential function e to the power x, you get the same function e to the power x. And then when you integrate a to the power x, where a is a positive constant and not equal to 1, you get a to the power x divided by log a. So it's important here that a to the power x dx, the conditions are important. A is positive and a is not equal to 1. So then only you get, when you integrate a to the power x, you get a to the power x divided by log a. Why is this condition important? Because log 1 is equal to 0, and you obviously, it doesn't make sense here because you would simply get 1 over 0, right? So it doesn't make sense, and that's why a is not equal to 1. And a is if a is equal to 1, you get log 1 0. If a is negative, then your log function is not defined, right? Is not defined. So it's important that you understand what your log function is. So your log function is only defined for positive x, right? And it cuts at x equals to 1, and it's 0. Log 1 is 0. Right. So that's why those two conditions are important. And these two, like I said, trigonometry, you don't need to worry. Right. Let's have a look at few basic examples now. We covered a lot of rules, and through examples only, it's you get used to using these rules, and that's important. So we are told, integrate a polynomial function. Suppose the cost function's marginal cost is given by this function as a function of output q. Find the total cost function. Now under differentiation, and I think I don't remember in your mid-sem whether I gave this, but under differentiation, what would happen is you're given the total cost function and you're asked to find the marginal cost. Under integration, you'd be given your marginal cost as a function of your output Q. And here we are asked to find the total cost. So remember, what is marginal cost? Marginal cost is when you differentiate your total cost with respect to Q, you get your marginal cost. That's what we know. So now we are asked to find, so we are given the marginal cost. We are given the marginal cost. We are asked to find the total cost, right? So basically we are asked to find the antiderivative of the marginal cost. How do we go about doing that? Very simple. You would integrate the marginal cost function with respect to dq. So what is marginal cost function? 6q squared minus 4q plus 10 dq. So now from the linearity rule, we can separate these out. What is the linearity rule? Let's go back and remind ourselves. The linearity rule is this. You had this one whole function, the integral of a sum function. So you can separate it out, sum of the integrals. So let's first do that. Let's first take these out and separate it out. 6q squared integrated with respect to dq minus integrate 4q with respect to dq plus integrate 10 with respect to dq. I separated out the function. Now after separating it out, what can I do? I can take out these constant values also out of the integral. 6, 4 and 10. So let's take them out. 6, then I have q squared dq minus, let's take 4 out. I have q dq plus I take 10 out dq. Then I use the power rule. What does the power rule say? It's just this over here. If I have a function x to the power n with respect to dx, if I have to integrate it, it says you take x to the power n plus 1 divided by n plus 1 plus the constant. Right, so I have a similar kind of thing here. Without x, I simply have q. So then q squared is, if I were to integrate it, q 2 plus q to the power 2 plus 1 divided by 2 plus 1 minus 4 times, here I have q to the power 1 plus 1 divided by 1 plus 1 plus 10 times. So here I have a constant which is either 10 or 1. So I simply have q plus, don't forget, the constant. Right. So what is this then? 6 cube over 3 minus 4q squared over 2 plus 10q plus c. Let's solve it a little bit more. So I have 2q cubed minus 2 times q squared plus 10q plus c. Now what were we doing all this time? We were finding the total cost function. This is the total cost function. So we were given the marginal cost, right? We were given the marginal cost and we were asked to find the total cost. And then when it's given, first remember what is marginal cost? Marginal cost is the derivative of the total cost. By how much does the total cost change with respect to your output? That is marginal cost. So now we are asked to find the aggregate. From the marginal cost, find me the total cost. So I would simply integrate the marginal cost. I go through two rules. One rule is the linearity rule and the second one is the power rule given the function. I use that and I find the total cost. So that's what I have done here in this particular example over here. So that's covering the rules of integration. Now we also have the next part, which is the second part, which is covering techniques of integration. Techniques of integration. So under techniques of integration, we are looking at two techniques, at least for this lesson. For this lesson, we are looking at integration by substitution. That's one technique. And the second technique that we're looking at is integration by parts. These are the two techniques that we are going to look at. So first, let's have a look at this integration by substitution. Integration by substitution. So we had a look at the rules, different rules we need to follow when we're integrating. That was the first section. The second section, we are looking at techniques of integration. So we are looking at two types of techniques. One is the integration by substitution and the integration by parts. So under the first technique, integration by substitution, it says here in the notes, substitution is used when an integrand or the function inside the integral contains a function and its derivative, making it look like an application of the chain rule in reverse. So for example, um, if you have a function, some function such that within that you have another function, and interestingly you see that the derivative of this function is over here. So this is multiplication, and you are asked to integrate this whole thing with respect to dx, right? So what did I say? Let me say that again, the whole thing again. You have a function f. Within that function, you have another function gx. And interestingly, this is multiplied by the derivative of gx. And you are asked to find the integral or the antiderivative of this. So in such a case, when you see something like this, what you would do is you take, so integration by substitution, you take, let's say, simple u as gx, right? Then you know, if you were to differentiate u with respect to x, you get g prime x, or in other words, you differentiate your function gx with respect to x, right? And then you see here du equals to g prime x dx. I simply took the dx to this side, okay? And now you see you're changing this whole function into a function from x into a function filled with u. Why is that? Because now you write this as f of u times g prime x dx. G prime x dx, you're going to put du and you're going to integrate this, right? So you're substituting your function which was in respect of x initially, and you're converting it to a function of u. And why do we do this? Simply to simplify our solving. That's why we do this. So let's have a look at an example. So we are looking at this particular example over here. Um, so we are looking at this example. We are asked to integrate 2x e to the power x squared, integrate it with respect to dx. Now, what's the first thing we have to do? So we are given this function. First thing we have to do is remind ourselves of what the rules are. So we have the linearity rule, which we can't use here. We have the power rule. Power rule also doesn't seem, I don't think we can use it directly. You have the constant rule. Well, the constant rule, what only thing we can do is take 2 out and then leave x times e to the power x squared dx, but it doesn't help. And afterwards, what do we do? Because these are multiplication. And then we have the exponential logarithm functions. No, yeah, there's an exponential here, but then it's multiplied with x. So what we learned here is only to the power x. We didn't have anything else. So nothing seems to work in terms of the rules that we had. So hence why we have this technique, integration technique by using substitutions. So what is the substitution we are going to use? So the first technique here that we learned about under substitution was if you had a function like this, you would use a substitution, let's say u, such that you transform your original difficult problem into a more simplified function. But identifying which substitution, which is over here, which substitution is the tricky part, right? That's the difficult part. So here in this example, I would identify my u as x squared. Now, that comes with solving this problem, obviously, and that experience I have of solving this. But see, if I take x squared as u, if I differentiate du by dx, I get 2x. Oh, so that's great. Why is that? Because then I have du is 2x dx. Isn't that what I have over here, right? So then I can simply go back to my original function, which was 2x e to the power x squared dx, right? I can rewrite it like this, e to the power x squared times 2x dx. And instead of 2x dx, I can substitute du. And instead of x squared, I can substitute u. That's what I am doing here. So then I'm transforming my problem from x, a function of x, into a function of u. Now this is very this we know how to integrate. Why is that? Because e to the power u, we have learned, it's this over here. E to the power u is your exponential function learnings that you got here, the first one. It's this one. E to the power x dx. That's what we have here. So here it's simply e to the power u plus a constant. But don't forget, you can't keep the final answer in terms of u. You substitute in what you had before. What was u? It was x squared. It's this value, x squared plus c. And that's the answer for this. So the tricky part in integration is identifying what technique to use. Is it integration by substitution, which was the case here? And for that, you need to, and I emphasize on this, you need to do a lot of sums for this, right? So that was one example. Let's see whether we have something else. So that's the answer you got here, ex e to the power x squared plus c. No, I don't have another example. I think there might be examples that we can follow later on. But let's move to the second technique. So the first technique we looked was integration by substitution. The second technique is, so that's what we looked at. Second technique is integration by parts. The second technique is integration by parts. Right. So integration by parts is also quite an interesting endeavor here. So we have two functions multiplied together, right? And we are looking at differentiating it, u of x times v of x. And we are looking at differentiating this with respect to x, because everything is in x. How did we do that under differentiation? Very simple. You take u times x out, and then you differentiate vx, plus you take vx as you treat vx as a constant, and you differentiate ux. Okay, that's fine. Now what we have to do is we are given this function, and we are asked to find this. How do we do that, right? So then if you further go along this idea, if I were to integrate, if I were to find ux vx, then I would be integrating, because I have to find these ux v prime x, plus Vx u prime x with respect to dx. Okay, and then what I have is I'm going to separate it out using the linearity rule, and I'm going to let go of this x because it's just there. It's simpler just to say u times v rather than saying u of x and v of x. I'm just going to say u times v, and here also u times v prime plus u times v prime dx plus v times u prime dx. So then you know that v prime, what is v prime? V prime of x, or I just call it v prime, that is simply dv by dx. U prime of x is u prime du by dx. So therefore, I can write u times v equals to u times dv by dx times dx plus v times du by dx times dx. And then uv, I can write this as u times dv plus v times du. Then if we are told to compute the integral of u dv, what we do is we make u dv the subject such that we take this to this side, uv times minus v du. So this final equation is what we have to keep in mind when we are looking at integration by parts. So let's look at an example. Because this proof, obviously I'm never going to ask proofs from you all. Let's look at an example. So this example we are looking at, integrate log x dx. That's what we looked at before as well, log x dx. Okay, first thing we have to figure out is, can we use any of the rules that we followed before? None of the rules will help us to integrate log x dx. Okay, then can we use a particular substitution that can help us out with? Because that was the first technique that we followed. As far as I know, there is no substitution where it can make us easier to solve this. Then the second technique we studied is this integration by parts. So integration by parts goes like this. So if I have log x dx, I would identify this as 1 times log x dx, because log x multiplied by 1, you get log x, right? Now, what does integration by parts tell me? I have to identify two things. The first thing is choosing u, which is the function you want to differentiate, and choosing dv, which is the function you want to integrate, right? So here I'm going to choose u, which is the function I want to differentiate, as log x, and I'm going to choose dv by dx as 1. When this happens, when I choose u as log x, then I have du by dx as 1 over x. And over here, I have v, which is equal to x. Why is that? After integrating 1 with respect to dx, I get x. Right. Now, according to this formula, u times dv. What is u times? U times dv by dx, which is log x times dv. That's what we have, equals to u times v. What was u? Log x. What is v? Times x minus integral of v times du. What is v? X times du is 1 over x dx. 1 over x dx. Now you see, you get x log x minus the integral of dx, which is x log x minus x plus c. So the log, so here dv log x dx, log x dx, right? So let's go through that example again. What did we have to do? We needed to figure out the integral of log x dx. Now, this is the hardest problem in integration that you will face. We had to figure out the integral of log x dx. What did we do first? We first have to see whether any of those rules, like linearity rule, the constant rule, the exponential and logarithmic rules, whether all of those rules help me to solve this. No, none of them do. Then I had to check, okay, I have learned two techniques. One technique is integration by substitution. Does any of substitutions help me with this? No, it doesn't. Then I go to the second method, which is the integration by parts method. So under integration by parts, I was told the equation that I have to use is u dv, which is equal to uv minus v du, which is this equation, right? Where I had to find a function u which I want to differentiate. I had to figure out u which I want to differentiate, and then I figure out a function dv which I want to integrate, right? So by differentiating, I want to simplify, and by integrating also, I want to simplify. I don't want to complicate matters. So when I'm given log x, I have to see log x as 1 times log x dx integral. Then I choose the function that I want to differentiate as u equals log x. Why is that? Because if I were to differentiate log x, I get 1 over x, and I get rid of this log factor. Because the ln factor is it's very annoying for me to integrate because I don't know that. And then from that, I know that du equals 1 over x dx. Then what is the function I want to integrate? The function I want to integrate is 1. Then then if I were to integrate both sides with respect to dx, I get v here equals to x. Right, now I look at my original equation over here. What does it say? U times dv. U times dv is log x times dv from here you can get is equal to dx. U times dx. That's what we need to find. Equals to u times v. Okay, u times v. X log x minus v times du. V times du. V times 1 over x dx. So here you see, because you chose u equals to log x and you differentiated it, that's what we did here in this block, and you chose dv, the function you want to integrate, as 1 in this block, and when that happens, this beautifully cancels out and you are left with x log x minus integral of a constant, and you know here it's 1 times dx, so a constant value to be integrated. From the integration rules, you know it's x plus the constant value c, which is what you get for log x dx. Now let's assume that I didn't choose u to be equals to log x. I chose u as equals to 1, and I chose dv by dx as log x. Now what do I do? Okay, if I differentiate du by dx, it's 0, that's fine. How do I integrate? How do I find v from this dv by dx? I had to integrate dv by dx with respect to dx, and I had to integrate log x also, because right hand side, left hand side, I had to do the same thing. Well, here I get v, but here again I get the same problem that I wanted to solve, which is v equals to integral of log x dx. So this kind of selection does not help me. Hence why when you're selecting the function u and dv, you have to find a function which you can differentiate, and dv a function that you can integrate, such that your problem becomes easier to solve. And that's what we have done here. Is there another example that we can follow? Yes, this is another example right at the bottom over here. So let's look at that example. Example number 2. So we are asked to integrate x times a to the power x dx. Right. Again, Do any of the rules help me? The linearity rule, the constant rule, the exponential rules? Not really, because exponential rule doesn't help because there's a multiplication of your exponential function with x. Linearity rule, no, there's no summations here. Constant rule, no, there are no constants here. Okay, techniques. Two techniques we learned. By substitution, yeah, let's try it out and see. So if I say, okay, u is equal to x, does it help? Du by dx is 1. Um, well, then du is equal to dx, and then x is u, e to the power u du. No, it's the same problem. Just that I've substituted x with respect with u, that's it. And I get the same problem. No, that doesn't help. So the substitution method, I can't find a suitable substitution that will help me. Okay. Then the next technique I have available with me is integration by parts. Here, choosing integration by parts, I know is a little tricky to do because I had to figure out the u function which I want to differentiate and the dv function which I want to integrate. So how do I choose my two functions? Okay, so I have two functions here, right? What were they? X times e to the power x. Now I want to simplify this. Now e to the power x, if I differentiate or integrate, I get e to the power x. There's no point of that, right? But if I take the function x and if I differentiate it, that makes life easier for me, doesn't it? So let's try that out. I take u to be my function x because if I differentiate, because u is the function I'm going to differentiate, if I take u and I differentiate it with respect to x, I get 1 such that du equals to dx. That seems to be good. Then I have dv by dx. I choose that, the function which I want to integrate. So if I were to integrate both sides with respect to dx, I get v here, and I get, if I were to integrate e to the power x with respect to dx, that's simply my exponential function rule on integration. I get e to the power x. That's it. Now, what was my equation? My equation was, let's go back to see. What's the u dv equals uv minus v du, u dv. So u dv, that's what I want to integrate. That's what I'm looking at. Equals to uv, u times v, okay, xex, minus v times du, v times du, these two. So v times du is dx. Oh, superb. Now I've gotten rid of that multiplication, because my problem here when I see this integration is that there's a multiplication here, right? X times e to the power x, and I can't do anything with that. So now I can. Now it's simply x e to the power x minus integration of e to the power x is e to the power x using the exponential rule plus c. But what if I chose differently? What if I chose u to be e to the power x and dv by dx to be x? What would happen then? Let's check it out. Du by dx then would be e to the power x. It doesn't do anything. And du would be e to the power x dx. Okay, e to the power x dx. I'm substituting it with du. That seems to be a good thing to do. E to the power x dx. But if I look at now, that's the differentiation part of it. If I look at the integration part of it, if I were to integrate both sides with respect to dx in order to get v, what happens? I get v here, x dx. So I'm going to use my rule. So x to the power n is 1. So I get x squared over 2. Um, now, okay, x squared over 2. Let's go ahead and see what I get then. Here I have u dv equals to uv. U is e to the power x, v is x squared over 2, minus v times du. That's the equation. I'm just simply putting it to this equation over here. right? uv minus integration of v times du. V is x squared over 2 times du is O, e to the x dx. So has my problem actually eased? No, not really. It has gotten harder now. Why is that? Because now I have the integration of x squared e to the power x dx, which is harder than the original problem, right? Because original problem only had x times e to the power x. Now I have x squared e to the power x. So see, the functions you choose is critical. So this method doesn't work, right? Where you choose the u, you must choose the u such that when you differentiate it, it simplifies like this over here. And then you choose the integral function such that, I mean, it's also, you're looking at simplifying it. When you choose it like that, your integration becomes much, much easier. So those are two very important techniques that we looked at. One was um, integration by substitution, right? That is, you change the variables to make the function look easier to solve. The second one was integration by parts. And for all of this, I have given problem sets in your Google Drive folder. If you go to problems and solutions, earlier I couldn't share the screen. I was showing this before at the onset of the lecture. Lecture 9, practice problems. I think I should have given a lot of problems here. Integration by substitution, integration by parts, some examples. And also not only these problems, I have given answers as well. Solutions for practical problems. Just go through the solutions and see whether it makes sense. So just do those problems and get a feel for this as well. It's very important practicing this. Then, so all this time we were talking about integration without those upper and lower bounds. Now we are coming to this integration of, within a given interval, you want to integrate. And when you integrate, just like in that video, what 3 blue, 1 brown explained, what we are getting is the area under the curve through integration. And that visual intuition which he gave, which I showed you through his video, is very, very critical. So now we are looking at definite integrals. When you say definite integrals, you are looking at a particular interval. So you have a upper bound, a lower bound, and an upper bound value in your integration function, right? So that's what I've given here. Now remember, even in that video they covered it, the fundamental theorem of calculus. So that's what we learn here, which is the most important. The fundamental theorem of calculus. So the fundamental theorem of calculus says if you have a function, a continuous function f of x, and if you want to integrate it with respect to dx from a point A to a point B, if an antiderivative exists, then if the antiderivative is f capital F, then your answer would be you substitute in the upper bound first to your antiderivative and you deduct the lower bound to your antiderivative. That's what the fundamental theorem of calculus tells you. For example, let's look at this particular example over here. So it says integrate the function 2x squared from 1 to 3 with respect to dx. So first things first, let's first integrate this. So I have 1 to 3. I take 2 out because it's a constant, x squared dx. Then what is x squared? I use the power rule very simply, which is x2 plus 1 divided by 2 plus 1. Now I put a bracket and I say my lower bound and upper bound. I don't need to put the constant now. Why? Because I have definite integrals. I know I'm given a particular interval at which I want to integrate it. So I have here x cube over 3 from 1 to 3. Then what does the fundamental theorem of calculus tell me? I take all the constant values out. The fundamental theorem of calculus tells me um, take the upper bound and substitute it, that is this value, and substitute it in the function that you got, minus take the lower bound and substitute it in the function you get. Lower bound is 1 and substitute it here. So what do I do? First I substitute in the upper bound, 3 cube, minus I substitute in the lower bound, 1 cube, right? And then what do I get? 2 over 3. 3 cube is 27, minus 1 is 26. This here gives me 26. 26 times 2 is 52. 52 over 3 is the answer when I integrate 2x squared times dx. And that's what I get here. So the difference between what we're doing now and what we did before is here we are given an interval in which you have to integrate. Therefore, you don't get that constant value because why? Earlier we got the constant value because you get a family of functions, and the family of functions, if you differentiate it, you get the integral, and therefore if you integrate it, you get the antiderivative with the constant. But here you have a definite integral with an upper bound and a lower bound. Therefore you do not, in these kind of problems, you do not need the constant because a definite integrals gives you an exact value. And then the properties of definite integrals is the same thing, same properties or rules that we looked at before, the linearity, additivity. Additivity is a little different. Additivity is telling us if I were to integrate a function f of x dx from a to b, and if I were to integrate that same function f of x with respect to dx from b to c, then I can simply, without doing all of this, I can say integrate that function f of x with respect to dx from a to c. A to c. That's what the additivity rule is telling me. The reversal of limits rule is telling me if I have a function f of x dx to with respect to dx, I'm integrating from a to b. If I were to change the two bounds and say, look, I want the function to be integrated with respect to dx from b to a, so I'm switching the two, then I have to remember to put a negative sign in front. That's very important. And then the zero interval, that is, I'm integrating at the same point, and that simply means you get 0, because if you remember, integration in under definite integrals, we are looking at areas under the curve. And how are we calculating these areas under the curve? By looking at these small rectangles. So what I'm saying here is, when I look at this one, a to a, I'm simply saying at that same point integrated. So at the same point, we don't have anything, just a line. There's no rectangle, just simply a line. So the area is 0 then, because for the area to exist, you have to have a height and a width. Um, right. I think, yeah, so let's just look at an example of this definite integral. A firm's marginal cost function, again, I'm given a marginal cost function, 5 plus 2q, and we are asked to say, what does it say? What is the increase in total cost when production rises from 10 to 15 units? Okay. So what is the increase in the total cost? Now, in the earlier section, we were asked to calculate the total cost. How do we do that? We integrate the marginal cost with respect to dq. But in this section, we are given two intervals where the production rises from 10 to 15 units. So it's a definite integral. It's called a definite integral. 10 to 15 units. What is the marginal cost? 5 plus 2q dq. So linearity rule first applies. Take 5 out. Dq, which is constant value 10 to 15 plus take 2 out, q times dq, 10 to 15. Don't worry about the upper and lower bounds until we find the antiderivative or the integral value. Here we get 5 times q, square bracket 10 to 15, plus 2 times q squared over 2, 10 to 15. So here I get 5 times. Fundamental theorem of calculus tells me to put the upper bound minus the lower bound in the antiderivative, which is q, plus here 2 cancels out, 15 squared minus 10 squared. So if I were to calculate that, I've given the answer, you might get 150, right? So that's the difference in the definite integral. So earlier we just simply calculated the marginal cost, the total cost, by finding the antiderivative of the marginal cost. But here we looked at an interval within which we integrated it. This section, you don't need to worry. Improper integrals, I've just given it for completeness sake, but I will not test it in the exam. It goes way beyond the knowledge you would need. So it's just there, but you can just simply ignore it. And if you're interested, you can read through it also. Then we just do applications of integration economics. Mainly it's marginal functions to total functions. That's what we're looking at. For example, marginal cost to total cost. That's one example. And marginal utility to total utility. That's another example. So likewise, and then we must have also studied consumer surplus and producer surplus. So we use integration to compute consumer surplus and producer surplus. You must have studied it in microeconomics. So for example, you have your quantity, your price, your supply, and your demand functions, and your market clearing price and quantity, the equilibrium. So what does consumer surplus tells? Well, look at the demand function. The consumer is willing to pay any of these prices for the given quantities, but the market clearing price is PE. So therefore, the consumer surplus is given by this area. Whereas the producer is willing to pay these prices for the given quantities, right? For the given quantities, but the market clearing price is PE. So therefore, the producer surplus is given by this area, right? So here you have consumer surplus, here you have producer surplus, and then you must have done these, but I'm not going to go into detail. You have price flows introduced, a price flow, and a price ceiling. And when you're introducing price flows and price ceilings, you get this deadweight loss, right? So you must have done this. So what's interesting is here in microeconomics, you would study very linear curves, right? Your supply and demand functions are always linear. But in reality, you don't get linear curves. It's always non-linear, and it's much more complicated also. Not just non-linear, it's much more complicated. Let's assume it's non-linear. Then how do you calculate the area under the curve? That's where you one of the use cases of integration, and that's where I say consumer surplus over here. So consumer surplus, if I were to draw this again, price, your demand function and your supply function and your market clearing price, consumer surplus is this part, right? So how do I do that? So if I was told my demand function is given by PD of Q, if this function is PD of Q, what I have to do is from 0 to Q, I would integrate my PD of Q. And what does that give me? If I were to integrate PD of Q from 0 to Q, that would give me the area under the curve. But which area am I getting? I'm getting this total area under the curve, under the demand function from 0 to Q. But I don't need the bottom part. Consumer surplus, remember I told you consumer surplus was this top triangle. So then I had to get rid of the bottom part. What is the bottom part? It's a square with a height of P and a width of Q. So I multiply P star. P star is the equilibrium price times Q star. And that's my consumer surplus, right? That's what I get here. Similarly, if my supply function, right? If my supply function, demand, supply, if my supply function is given by this PSQ, and Q star and P star are my market clearing functions. Remember I told you this area is the producer surplus. Now how do I calculate that? Well, if I were to integrate my supply function with respect to dq from 0 to q, what would I get? If I were to integrate my supply function from 0 to q, it's the area under the curve. What is the area under the curve? I would get this area, right? But that's not what I want. I want that little triangle that I've highlighted. How do I get that? Well, if I can take the area of this whole square, which is P star times Q star, and I deduct this red area, which I covered, which is given by this red area, then I would get the triangle area, which is producer surplus. So now I have generalized producer surplus and consumer surplus for you all, such that you take any nonlinear function, you can find your producer surplus and consumer surplus, rather than simply looking at linear functions and looking at the areas under the curve or triangles in that manner. So that's an interesting application that you can use for integration. That's mainly what I wanted to talk about. There are more applications that you can read through in from your note. I've given a note, but those are all applications. Um, this section we don't need to worry too much because we are going to look at it at differential equations. So you don't need to worry too much. I've given this as an intro, which we can look at next week also. Then we're done with the lesson. You have given a lot of practice problems here as well. And I have given some worked examples with some solutions. So go through all of this. Integration is actually, I would say, one of the harder problems, harder sections if you have not done any calculus at all. So I would really, really urge you to do a lot of problems, because what I saw in the midsem paper also was, I told you all this last week, in the midsem, I didn't check your math. I did not check your mathematics knowledge. I checked whether you were able to map a similar type of problem I had given in the model paper into a question in the midsem. All were mostly very similar. Mm. And also there also I saw that a lot of students had lost marks because obviously maybe you're not very familiar with these concepts and it's very new to you. So um, how you learn these areas is you first get an intuition behind it, and that's why I show these videos, and you should also watch these videos to get a visual understanding. It's very simple visual understanding, and then you get into the crux of it through the algebraic calculations. And when you're doing that, you need to write it down. Don't do it in your head. You need to write it down, and you need to do a lot of practice problems. And integration is key, because if you take the whole module of this MEcon quantitative economics, you have differentiation, you have matrices, you have integration, you have differential equations. Everything's nicely connected, but you will never see that connection if you're not familiar. So you have to do a lot of problems. So that's where I would leave you today. That's the end of the lecture. If you have any questions, do please drop me an email, and make sure I marked your midsem papers. Make sure you reach out to Professor Singh and you request for your marks. That's it. Thank you very much.